Guys, now let's start the chapter electromagnetic induction. See, first of all, the introduction part is not required, and there are three experiments, and the first experiment explanation at present is not required. See, this is the experiment, that is when the bar magnet is pushed towards the coil, the pointer in the galvanometer G deflects. So what does this tell? It shows that the relative motion between the magnet and the coil is responsible for generation, that is induction of electric current in the coil. And the second experiment is that this is the second experiment, and the current is induced in the coil 1. Current is induced in this coil 1 due to the motion of the current coil C2. See, what it tells is that when the coil C2 is held fixed and C1 is moved, the same effect are observed, and again it is relative motion between the coil that induces EMF in the current. It's simple, like when the current is flowing in this and it moves towards this coil, galvanometer deflects, that is shows current. But the third experiment is very important. What does it tell? The above two experiments involve relative motion between a magnet and a coil and between two coils respectively. Through another experiment, Faraday showed that his relative motion is not an absolute requirement. This relative motion is not an absolute requirement because it shows that because in this figure it shows that two coils C1 and C2 are held stationary. Coil C1 is connected to galvanometer G while second coil C2 is connected to a battery and a tapping key. It is observed that the galvanometer shows momentary deflection when the tapping key is pressed. The pointer in the galvanometer returns to 0 immediately. If the key is held pressed continuously, then there is reflection in the galvanometer. When the key is released, a momentary deflection is observed again, but in opposite direction. It is also observed that the deflection increases dramatically when an AND rod is inserted into the coils along the axis. Now let us study about magnetic flux. See, what happens in that is that a plane of area A is placed in uniform field B, and with this one, that is a plane of surface A is placed in uniform magnetic field B, and it can be written as chi B equal to B into A equal to BA cos theta, where theta is the angle between B and A, and the notion of area as a vector has been discussed in the chapter 1 from that equation, and can be extended to curved surface and non-uniform fields. And if the magnetic field has different magnitudes and direction at various parts of the surface as shown in this figure, then a magnetic flux to the surface is given by phi B equal to B1 into dA1 plus B2 into dA2 plus all, that is summation of all plus all, which gives summation of all equal to BI into dAI, where all, that is this all, this all stands for summation over the area element dA1 comprising the surface, and B1 is the magnetic field at the area element D1, and the SI unit for magnetic flux is Webner VB or Tesla meter square. Magnetic flux is a scalar quantity. Now let us study about Faraday's law of induction. See here, magnetic field B at the ith area, consider area ith area element, and dA1 represents the vector of the ith area element, and this is the field and this is the vector represented. And see what is Faraday's law of induction. The Faraday stated experimental observation in the form of law called Faraday's law of electromagnetic induction. It is stated as below: the magnitude of induced EMF in a circuit is equal to time rate of change of magnetic flux to the circuit, and it's mathematically the induced EMF is given by epsilon, that is equal to minus d phi b divided by dt. The negative sign indicates the direction of epsilon and hence the direction of the current in closed loop. This will be discussed in detail in next section. In the case of closely wound coil of n turns, change of flux associated with each turn is same. Therefore, the expression for total induced EMF is given by epsilon equal to minus n d phi b divided by dt. And the induced EMF can be increased by increasing the number of turns n of a closed coil. From equations 6.1 and 6.2, the previous equation which I'll show, this one, equation 6.1 and 6.2. In this equation 6.1 and 6.2, we see that the flux can be varied by changing any one or more of the terms B, A and theta. The experiment 6.1 and 6.2 in section 6.2, the flux is changed by varying B. The flux can also be altered by changing the shape of the coil, that is, by shaking it or stretching it in a magnetic field, or by rotating a coil in magnetic field such that the angle theta between B and A changes. In this cases 2, an EMF is induced by the respective coils. Now let us do an example. Consider experiment 6.2, that is this experiment 6.2. What would you obtain? What would you do to obtain a large deflection of galvanometer? How would you demonstrate the presence of induced current in the absence of galvanometer? Now in this example 6.1, consider that experiment. Okay, we did that. Now the solution to that is to obtain large deflection, one or more of the following can be taken. That is, first one, use a rod made up of soft iron inside the coil 2, and 2 is connect coil to a powerful battery, and 3, move the arrangement rapidly towards the test coil C1. Replace the consider the second one. How would you demonstrate the presence of induced current in absence of galvanometer? Replace the galvanometer by a small bulb, the kind of one which you find in small torchlight. The relative motion between the two coils will cause the bulb to glow and demonstrate the presence of induced current. In experimental physics, one must learn to innovate. Michael Faraday is ranked as one of the best experimentalists ever, was legendary for his innovative skills. Now let's come to the next example. A square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. A uniform magnetic field of 0.10 Tesla is set up across the plane in northeast direction, and the magnetic field is decreased to 0 in 0.70 seconds at steady rate. Determine the magnitudes of induced EMF and current during this time interval. So let's see how. Okay. First of all, the angle theta made by the area vector of the coil with the magnetic field is 45 degree. From equation 6.1, the initial magnetic flux is phi equal to BA cos theta. So you need to find what is BA cos theta. See, you know what is cos 45 degree, 1 by root 2. And this one is BA. It's 10 centimeter area, so 10 into 10 raised to power minus 2 Weber. And you need to you also know what is magnetic field. See, this the area is 10 centimeter, so when you convert it into meter, it is 1 into 10 raised to power minus 2. 10 becomes 1 because it's meter. And this one is 0.1, that is the magnetic field. Then the final flux is phi minimum equals 0. Change in flux brought about in 0.70 seconds. From equation 6.3, the magnitude of induced EMF is given by this E epsilon equal to phi delta phi B modulus of delta phi B divided by delta T equal to modulus of phi minus 0 divided by delta T equal to 10 raised to power minus 3 divided by root 2 into 0.7. The answer which you get is 10 raised to power minus 3, and you know what is delta T, 0.7. Answer is 10 raised to power minus 3 divided by root 2. Answer of this. Then this becomes the final answer. And the magnitude of current is I equal to epsilon divided by R, that is 10 raised to power minus 3 divided by 0.5 ohm. See, this is millivolt. So when you convert millivolt to volt, add 10 raised to power minus 3. And the resistance, as you know, is 0.5, is given 2 milliampere. So note that the Earth's magnetic field also produces a flux to the loop, but it is a steady field, that is, which does not change within the time span of the experiment, and hence does not induce EMF. Now let us study the next example. That's example 6.3. A circular coil of radius 10 cm, 500 turns and resistance 2 ohm is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about its vertical diameter to 180 degree in 0.5 seconds. Estimate the magnitudes of EMF and current induced in the coil. Horizontal component of Earth's magnetic field at the place is 3.0 into 10 raised to the power minus 5 Tesla. The solution. Initial flux to the coil, phi B initial equal to BA cos theta, that is 3.0 into 10 raised to power minus 5 into pi into 10 raised to power minus 2 into cos 0. The values, substitute the values over here. Okay, now the field is given over here, that the magnet field is placed at 3 into 10 raised to power 5 Tesla, it's given, and Radius is 10 centimeters. So to find the area, pi r square, that is pi into 10 raised to power minus 2 r square, pi r square. Okay, pi r. Radius can also be considered as pi r because it's a circular coil. I feel it's cut into half, so just pi r, not pi r square. This is the answer. Final flux of the rotation phi b final is 0.3.7 10 raised to power 5 is same thing, cos 180 degree, and therefore the estimated value of induced EMF is epsilon equal to n into delta phi divided by delta t, and you know n is 500 and 500 turns it's given, and into 6 pi 10 raised to power minus 7 is delta phi divided by time, so 0.25, and this is the answer. See over here, delta phi is this plus this, that is it comes 6 pi and 10 raised to power 7, and so divided by the time interval, and you get the answer. And see next one, that is I equal to epsilon divided by r, you get the answer, divided by resistance. Note that the magnitude of epsilon and I are estimated values, and their instantaneous values are different and depend upon the speed of the rotation at a particular instant. Okay, now let's go to the next one. So the next concept is Lenz's law and conservation of energy. Lenz's law states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produces it. I hope you understood. And you know, in this it's the illustration of Lenz's law, and this and this note that the direction, this indicate the direction of induced current, that is this is north and this is south. The shapes also indicates that. Now let's solve the first example 6.4. What it tells is that the figure 7.4 shows the planar loop of different shapes moving out of or into the region of magnetic field, which is directed normal to the plane of the loop away from the reader. Determine the direction of induced current in each loop using Lenz's law. See, this is the figure, and it is shown that different shapes, it moves in, comes out, and you have to prove that using Lenz's law. Okay, solution. See, if in the first figure the magnetic flux to the rectangular loop ABCD increases due to the motion of the loop in the region of magnetic field, and the induced current must flow along the path BCDAB so that it opposes the increasing flux. And you know in this figure B, due to the outward motion, magnetic flux to the triangular loop ABC decreases, due to which the induced current flows along BACB so as to oppose the change flux. And in this figure, as the magnetic flux decreases due to motion of the irregular shaped loop ABCD out of the region of magnetic field, the induced current flows along CDABC as to oppose the change in flux. Note that there are no induced current as long as the loops are completely inside or outside the region of the magnetic field. Understood? Now let's come to the next example, that is example 6.5. There are three questions. That is, a closed loop is held stationary in magnetic field between the north and south pole of two permanent magnets held fixed. Can we hope to generate current in the loop by using strong magnet? First, let us solve this. And its answer, no. However strong the magnet may be, the current can be induced only by changing the magnetic flux to the loop. Question B. A closed loop moves normal to the constant electric field between the plates of large capacitor. It is current induced in the loop. Is a current induced in the loop? First one, when it is wholly inside the region between the capacitor plate, and when it is partially outside the plates of the capacitor, the electric field is normal to the plane of the loop. Okay, the answer is no current is induced in either case. Both the case no current is induced, because current can not be induced by changing the electric flux, as simple as that. Okay, see question. Rectangular loop and circular loop are moving out of a uniform magnetic field region, that is given in figure 6.8, which I'll show you back, to a field free region with a constant velocity. In which loop do you expect induced EMF to be constant during the passage out of the field? The field is normal to the loop. See, this is the figure. We need to, okay, let me answer that. This is the figure as I told, and the induced EMF is expected to be constant only in the case of the rectangular loop. In case of circular loop, the rate of change of the area of the loop during its passage out of the field is not constant, hence induced EMF will vary accordingly. Okay, now predict the polarity. D question. Predict the polarity of capacitor in the situation described by figure 6.9, that is this. And what is its answer? The polarity of plate A will be positive with respect to the polarity of the plate B of the capacitor. Okay, now let's come to the next topic, that is motional electromotive force or motional EMF. So first let us consider this figure, and this is the length of the conductor and it moves with velocity v, and this is the breadth x. The arm PQ is moved to left side, thus decreasing the area of rectangular loop, and this movement induces current I as shown. Now this one, phi b equal to blx. Suppose since x is the change is changing with time, the rate of change of flux, phi b will induce an EMF which is given by epsilon equal to minus d phi b divided by dt equal to minus d blx, that is d phi b divided by dt, and you get this blv. Now here we have used dx by dt equal to minus v, which is speed of the conductor pq, and this induced EMF blv is called emotional EMF, and w equal to qv into bl, and since EMF is the work done per unit charge, then it becomes like this: epsilon equal to w by q equal to blv, and here you can see F equal to q of E plus B into E, that is q into E. Yes, now let's solve this example. 6.6. A metallic rod of 1 meter length is rotated with a frequency of 50 rev per second, with one end hanging at the center and the other end at the circumference of the circular metallic ring of radius 1 meter, about an axis passing to the center and perpendicular to the plane of the ring. Figure 6.11. I'll show it now. A constant and uniform magnetic field 1 Tesla parallel to axis is present everywhere. What is the EMF between center and the metallic ring? Let us turn and see what it is. As you can see, it's a huge figure over here. Let us zoom and see. And this is the figure, this is metallic ring, and it possesses an angle omega, and theta equal to omega t, and this is the radius r, q and o are the points. The solution: there are two methods. One is method 1 and another one over here is method 2. Let us start. Now as you can see, as the rod is rotated, free electrons in the rod move towards the outer end due to Lorentz force and get distributed over the ring. Thus the resulting suppression of charges produces an EMF across the end of the rod. At a certain value of EMF, there is no more flow of electrons and a steady state is reached. And equation 6.5, this is equation 6.5. The magnitude of the EMF generated across the length dr of the rod as it moves at right angles to the magnetic field is given by d epsilon equal to bv dr. Hence epsilon equal to integration of d epsilon integral from 0 to r bv dr equal to integration from 0 to r b omega dr equal to b omega r square divided by 2. Note that we have used, that is v equal to omega. This gives omega equal to, you can see, half into 1 into 2 pi into 50 into L square, and this is the answer. And there's another method which you can try, that is to calculate EMF. We can imagine a closed loop of OPQ in which point O and P are connected with the resistor R, and OQ is the rotating rod. The potential difference across the resistor is then equal to the induced EMF and equals to B into rate of change of area of the loop. If theta is the angle between the rod and the radius of the circle at P at time t, the area of the sector O PQ is given by pi r square into theta divided by 2 pi equal to half r square into theta, r is the radius of the circle. Hence induced EMF is epsilon equal to b into d by dt of half r square theta, which is equal to half b r square d theta divided by dt equal to b omega r square divided by 2. Note that d theta divided by dt equal to omega equal to b pi v. This expression is identical to the expression obtained by method 1, and we get the same value of this one, epsilon. Now let's try example 6.7. A wheel with 10 metallic spokes, each 0.5 meter long, is rotated with speed of 120 rev per minute in a plane normal to the horizontal component of Earth's magnetic field He at a place. If He is 0.4 galvins, that is G, at a place, What is the induced EMF between the axle and the rim of the wheel? Note that 1g equal 10 raised to power minus 4 Tesla. So solution, induced EMF equal to half omega b r square, which is equal to half into 4 pi into 0.4 into 10 raised to power minus 4 into 0.5 square, which is the answer. The number of spokes is immaterial because the EMF across the spokes are in parallel. Let us learn the next topic, that is energy consideration of a quantitative study. So this formula I equal to E divided by R equal to BLV divided by R, and this force L of L into B is directed outwards in the direction opposite to the velocity of the rod. The magnitude of the force is F equal to ILB equal to B square L square divided into V divided by R. We have used equation 6.7. This equation 6.7. Note that this force arises due to the velocity of the charges responsible for the current along the rod and consequence of Lorentz force acting on them. Alternatively, the arm PQ is being pushed with constant speed V, and the power required to do this is P equal to F into V, that's equal to B square L square V square divided by R. Now the another formula is PJ, P of J, that is pass in power in joule lead, equal to I square R equal to B into L into V divided by R the whole square into R equal to B square L square V square divided by R. And this is the most important, that is modulus of epsilon equal to delta pi V divided by delta T. However, modulus of epsilon equal to IR equal to delta Q divided by delta T into R. Thus, most important is delta Q equal to delta phi B divided by R. Okay, now let us solve example 6.8. Now if you refer to this figure, the arm PQ of the rectangular conductor is moved from x equals 0 outwards. The uniform magnetic field is perpendicular to the plane and extends from x equals 0 to x equal to b, and is 0 for x is greater than b. Only the arm PQ possesses substantial resistance R. Consider the situation when the arm PQ is pulled outwards from x equals 0 to x equal to b and then is moved back to x equals 0 with constant speed v. Obtain the expression for the flux, the induced EMF, the force necessary to pull the arm, and the power dissipated as joule. Sketch the variation of the quantities. So this is the diagram or the solution. See, first of all, let us consider the forward motion from x equals 0 to x equal to b. Here the flux pi be linked with the circuit SP QR is phi b equal to BLX, and you know x is between 0 and b, and provided x is equal to 0 and BL and is also equal to BLB, that is x comes between b and 2b, provided x is equal to b. The induced EMF is epsilon equal to minus d phi b divided by dt, which is equal to minus BLB, provided x is same thing, provided the same condition equal to 0. Now what happens is that when the EMF is non-zero, the current I of magnitude I equal to BLV divided by R, and this is the graph, which I don't think is very important, outwards and inwards graph. And the force required to keep the arm PQ in constant motion is I into L into V, and its direction is to the left, and its magnitude F equal to B square L square V square V divided by R, and the same condition equal to 0. And Joule's laws of heating, apply the formula and get the answers. It's just simple. Once you obtain similar condition for the inward motion for x equal to b to x equal to 0, one can appreciate the whole process by examining the sketch of various quantities displayed in that figure. Okay. Now let us study the most favorite concept of everyone, that is eddy current. Did not learn this, just refer the diagram. Let us see in this, these are two bar magnets and these are copper plates, and eddy currents are generated in the copper plate while entering and leaving the region, and in this direction eddy current is generated. So what happens when eddy current is generated? When eddy current is generated, heat is dissipated, heat loss occurs, due to which, if heat loss occurs, example in transformers, overheating takes place, which is a problem, and a lot of energy gets dissipated. And this is a method to reduce eddy current, that is cutting the slots of copper plate, reducing the effect of eddy current. When you cut it, the eddy current just revolves around this, so you can cut. But you know, there are some uses of eddy current, that is eddy currents are advantages in certain applications, like one is magnetic braking in trains, electromagnetic damping, and induction furnace, electric power meters. So let us study them one by one. Magnetic braking in trains. Strong electromagnets are situated above the rails in some electrically powered trains. When the magnets are activated, the eddy current is induced in the rails opposite which opposes the motion of the train. As there are no mechanical linkages, the braking effect is smooth. Got it? Electromagnetic damping. Certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates, the eddy currents are generated in the core opposite to the motion and brings the coil to rest quickly. Induction furnace. Induction furnace can be used to produce high temperature and can be utilized to prepare alloys by melting the constituent metals. A high frequency alternating current is passed to the coil which surrounds the metals to be melted. The eddy current is generated in metals, produces high temperature sufficient to melt it. Now electric power meter. The shiny metal disc in electric power meter, analog type, rotates due to eddy current. Electric currents are induced in the disc by magnetic field and produced by sinusoidally varying current in the coil. Have you observed it rotating? Yes, of course. Inductance concept, and in that N5B is proportional to I. And inductance is a scalar quantity. It has dimension m, L square, t raised to power minus 2 and a raised to power minus 2, given by dimensions of flux divided by dimensions of current. And the SI unit of inductance is Henry and it's denoted by H. It is named in the honor of Joseph Henry, who discovered electromagnetic induction in USA, independently of Faraday in England. See, in mutual inductance, all of this is not required. This diagram you might remember if you want. Two long axial solenoids of same length. This example explains everything. Now let us try this. Two concentric circular coils, one of small radius r1 and the other of larger radius r2, such that r2 is much greater than r1, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. See, what happens is that let the current I2 flow through the outer circular coil, and the field at the center of the coil is B2 equal to mu naught I2 divided by 2R. Since the other coaxial is placed coil has a very small radius, B2 may be considered constant over the cross-sectional area. Hence, phi 1 equal to pi R1 square B2 equal to mu naught pi R1 square divided by 2 R2 into I2, and this is the answer. Not the answer, it's actually the formula M12 I2. Thus M12 equal to mu naught pi R1 square divided by 2 R2, and from equation 6.14, and that is this equation 6.14, M12 equal to M21 if you consider M. So they are equal and equal to this. Note that when we calculate M12 from an approximate value of phi 1, assuming that the magnetic field B2 to be uniform over the area pi R1 square, however, we can accept the value because R1 is or R2 is much greater than R1. Okay. Now all of this derivation is not required. Just remember this formula, that is epsilon 1 equal to minus m di2 divided by dt. Okay. Now let's learn the concept of self-inductance. In the previous subsection, we consider flux in one solenoid due to current in the other. It's also possible that EMF is induced in single isolated coil due to change in flux to the coil by the means of varying current through the same coil. This phenomenon is called self-inductance. In case flux linkage to the coil N turns proportional to the current through the coil, it is expressed as, no, this is not required. I already told the proportionality, that is N5B is proportional to I, so N5B equal to Li, which is also equal to mu naught N square A Li, and epsilon equal to minus L di divided by dt. Here there's a formula which is given, which is important. You need to remember, that is L, which is self-inductance, equal to mu R into mu naught into N square into A into L. Now another formula is W equal to half Li square. Now let us try this example. See, A, obtain the expression for magnetic energy stored in solenoid in terms of magnetic field. B, area and length L of the solenoid. How does this magnetic energy compare with the electrostatic energy stored in the capacitor? From equation 6.19, that is this equation, W equal to half Li square. W, or also called UB, potential energy, equal to half Li square, and you just derive this because B equal to this and keep on deriving, and at last you get a condition. Okay, I'll read it for you. Equal to half L of B divided by mu naught M the whole square, since B equal to mu naught Ni for the solenoid, and half of mu naught into N square into A into L of B divided by mu naught into N the whole square, equal to half 2 mu naught into B square into A into L is the answer. And the magnetic energy per unit volume is small u B equal to capital U B divided by B, where V is the volume that contains flux, equal to UB divided by A into L equal to B square divided by 2 into mu naught. We have already obtained the relation for electrostatic energy stored per unit volume in parallel plate capacitor. That is small u equal to half epsilon naught into A square. In both the cases, energy is proportional to square of the field strength, and equations 6.20 and 2.77 have been derived for a special case, a solenoid and a parallel plate capacitor respectively, but they are generated and valid for any region of space in which a magnetic field or an electric field exists. Now let us learn the concept of AC generator. Here, as you can see, the chapter which you learned in 10th class, I guess, is AC generator. These are slip rings, coil, axle which is attached to slip rings, and these are carbon brushes and alternating EMF. Now the basic element of an AC generator are shown in this figure, and it consists of a coil mounted on a rotor shaft, and the axis of rotation of the coil is perpendicular to the direction of magnetic field. The coil, also called armature, is mechanically rotated in uniform magnetic field by some external means. The rotation of the coil causes magnetic flux through it to change, so an EMF is induced in the coil. The end of the coil are connected to an external circuit by means of slip rings and brushes, and the coil is rotated with constant angular speed omega, and the angle theta between magnetic field vector B and area vector A of the coil at instant t is theta equal to omega t, assuming theta equals 0 and t equals 0. As a result, the effective area of coil expressed to the magnetic field line changes with time. According to expression 6.1, the flux at any time is phi equal to BA cos theta, and here BA is equal to BA cos omega t because theta equal to omega t. Now the next expression, thus the instantaneous value of EMF is epsilon equal to NBA omega sine omega t, where NBA omega is the maximum value of EMF which occurs when sine omega t is equal to plus or minus 1, which we denote sine, not sine, NBA omega as epsilon. Then omega equal to omega naught sine omega t. Since the value of sine function varies between plus 1 and minus 1, the sign or polarity of EMF changes with time. Note that from this figure 6.17, the next figure, as you can see, this is 6.17 figure, and I'll come that the EMF has extremum value of theta equal to 90 degree or theta equal to 70 degree as change of flux is greatest at this point. The direction of current changes periodically, and therefore the current is called alternating current, since omega equal to 2 pi nu, and according to equation 6.22 can be written as epsilon equal to epsilon naught sine 2 pi omega t. This is equation 2.3, and equation 2.2 is this. Now where nu is the frequency of revolution of generation coil. Now note that the equation 2.2, 6.22 and 6.23 give the instantaneous value of EMF, and epsilon varies between plus epsilon naught and minus epsilon naught periodically. We shall learn how to determine the time averaged value of alternating voltage and current in the next chapter. Let us see the steps in AC generation. That is, stage 1, the plane of the armature is perpendicular to the magnetic field. Stage 2, when the armature rotates to 90 degree, the plane of the armature is parallel to the magnetic field. And in stage 3, armature after rotation is 180 degree. And stage 4, armature after rotation of 270 degree. And stage 5 is armature after rotation to 360. Simple, just the rotation, and this is the graph. Did not remember it for exam point of view, it's just for your knowledge. In commercial generators, the mechanical energy required for rotation of armature is provided by water falling from a height. For example, from dams, they are called hydroelectric generators. Alternately, water is heated to produce steam using coal or other sources. The steam at high pressure produces rotation of armature, and these are called thermal generators. Instead of coal in nuclear fuel is used, we get nuclear power generator. Modern days generator produce electric power as high as 500 megawatts. That is, one can light up 5 million 1000 watt bulbs. In most generators, the coils are held stationary, and it is electromagnets which are rotated. The frequency of rotation is 50 Hz in India. In certain countries such as USA, it is 60 Hz. Now let us solve the last question of the chapter. and that is Kamla paddles. Consider Kamla paddling a stationary bicycle. The paddle of the bicycle are attached to a 100 turn coil of area 0.10 meter square. The coil rotates at half a revolution per second and it is placed in a uniform magnetic field of 0.01 Tesla perpendicular to the axis of rotation of the coil. What is the maximum voltage generated in the coil? The resolution voltage is given 0.5 Hz and N I hope you know, or 100 A is 0.1 meter square and B is 0.01 T. Employing equation 6.21, and this is the equation, add it and maximum voltage is this. Yeah, that's it. And let's discuss some summary. Those are some important points. You see, Faraday's laws of induction implies that EMF induced in coil of N turn is directly related to rate of change of flux to it, and that is epsilon equal to minus n d phi b divided by dt, and phi b is the flux linked to 1 turn of the coil if the circuit is closed, and current I equal to epsilon divided by R is set up in it, where R is the resistance of the circuit. When a metal rod of length L is placed normal to the uniform magnetic field B and removed with velocity V perpendicular to the field, induced EMF called motional EMF across its ends is epsilon equal to BLV. Now let us see some important points to ponder. Electricity and magnetism are intimately related. In early part of 19th century, experiments of Ørsted, Ampere and others established that moving charges current produce a magnetic field. Somewhat later, around 1830, the experiment of Faraday and they demonstrated that moving magnets can induce electric current. In closed circuit, electric currents are induced so as to oppose the changing magnetic flux. It is per the law of conservation of energy. However, in the case of open circuit, an EMF induced because it's end. How is it related to flux change? The motional EMF discussed in section 6.5 can be urged independently from Faraday's law using the Lenz's law on moving charges. However, even if the charges are stationary and Q of V into B term of the Lorentz force is not operative, an EMF is nevertheless induced in the presence of time-varying magnetic field. Thus, moving charges are in static field and static charges in time-varying field seem to be symmetric situation for charges in time-varying field seem to be symmetric situation for Faraday's law. This gives a tantalizing hint on the reluctance of principle of relativity of Faraday's law. The motion of copper plate is damped when it is allowed to oscillate between the magnetic pole pieces. How it is damping force produced by eddy current. Okay, here the chapter ends. Thank you for watching. Okay guys, as I always told and will always be telling that solving question is the most important part. You must solve questions like this and must be perfect in that. It clears all of your concepts. Thank you for watching. Happy learning. These are its answers. Thank you. Okay guys, if you like my video, do hit the bell icon and subscribe button so that you will be notified with all upcoming videos, which is fully free, and enjoy unlimited lectures. Thank you.